microscopic, macroscopic description, but we only have so much time, and given the constraints of the course, we only have so much machinery that we're allowed to use. So resistance is specifically a quantity measured in ohms that is a resistance to the flow of current. Resistance to the flow of current. And macroscopically, we imagine that there's a current flowing through a wire and that there are positive charges flowing with the current. Now really we know that there are negative charges flowing in the opposite direction, but just so that we don't have to worry about all those little sign flips, we just say that there are positives going in this direction. Microscopically, what's happening is that a charge, now for this it's harmless to do positive or negative, because these atomic cores on the outsides have electrons that will electrically repel negative charges, but as you get closer, the positive charge will also repel, and there's also quantum effects and stuff like that. So it will bounce off any moving charge usually. So the thing is being accelerated, but then it's bouncing back and forth. And on average, it's only drifting to the right, say. On average, the velocity is just drifting to the right, and we call that the drift velocity. So in principle, the current is really a vector that is essentially many particles of this charge traveling at some drift velocity. That's not really what it is, but that's kind of what you're describing. So then we have, now, given a certain amount of material, if we have a longer amount of material, then these little balls, these charges are going to make more bounces, which means they'll make more collisions, which means they'll lose more energy as they go from one end to the other. And that means it's harder for a charge to move from one end to the other. And that means that if we have our traffic jam of charges, it's going to be harder for charge to enter because it's harder for charge to get out, because it's, so hard to think of it like a pipe with a tiny diameter versus a pipe with a big diameter. And so the longer the pipe, the more resistance. Now what's interesting is that if I have a wider pipe, there are more lanes that they can go through, and it turns out that it's easier for them to pass through and find in the material the path of least resistance. And also the density of the atomic cores plays a role in the resistance, and so we can associate a given material with what's called a resistivity. It's a lowercase rho. The tube has a cross-sectional area A, it could be a square or something, and a length, so that the resistance of this piece here, as stuff goes through it this way, is rho times L over A. So the resistance of the wire increases with length, decreases with cross-sectional area, and increases with the material resistivity. Now this is, in our conventions, we will take that a piece of copper wire has effectively no resistance at all, but it actually does have some resistance. It's a very small resistance. It's a very small resistance that only becomes relevant if the current flowing through it becomes enormous. But usually we'll basically ignore the resistance. But you can in fact measure, if I have a long length of copper wire, you can actually literally measure the diameter, you can literally measure the length, you can know what the resistivity is for copper, and then you can check that that's true by taking an ohm meter and putting one end on one end and one end on the other end, and you will see that it has the correct amount of resistance. So the distinction, I don't know that this isn't entirely true. Okay, this is to first approximation, very roughly. The distinction between conductors, semiconductors, and insulators, in my opinion, is mostly a statement about resistivity. So at room temperature, where the resistivity is always given in ohm meters, because this is ohms, this is meters squared. So this is inverse meters, so this has to be ohms times meters. For conductors, copper is 1.68 times 10 to the negative 8 ohm meters. Tungsten is a little bigger. I may have mentioned that light bulb filaments are often tungsten. Iron is actually almost an order of magnitude larger than that of copper, so that's why you don't make circuitry out of iron. Mercury is an entire order of magnitude above that, which is why mercury may have good heat conductivity and thermal expansion properties, but you don't want to use it for conducting electricity. And then the semiconductors are within this intermediate range, all the way from 10 to the negative 5 up to about 10 to the 1, or sorry, 10 to the 0. Or I guess 10 to the 1 from the 60. Okay, so it's an enormous range, and then you're sort of in an intermediate range. Carbon is a semiconductor, but silicon is right in the middle. There's also germanium. I didn't put it on the list. It's all in the textbook. There's what the red table is. And then the insulators, you have glass and hard rubber. It's often said that glass doesn't conduct electricity. It's not entirely true. It can, but it's very resistant to conducting a current. And so the resistivity is 10 to the 9th to 10 to the 12th. What that means is if I have if the length divided by the area is a meter, then that piece of material of glass will have a resistance of about 10 to the 10, which is enormous. It's huge. So it effectively will let almost no current pass through. Hard rubber is even more. So when you have people who are working on, high voltage electrical lines, they'll be covered in a rubber suit because it's very resistant to the flow of current. Okay, now also resistivity does change with temperature. And so how it changes with temperature is pretty complicated. But if we linearize, if we look at just very small temperature changes, the variation is approximately linear. And so if we want to know what the resistivity at a temperature is, we take the resistivity at some reference temperature that's not 0, it's just a reference. Usually this is taken to be T0 is usually 20 degrees Celsius, which is about room temperature. And this is going to be 1 plus some constant alpha times the temperature difference. So this is just a statement that it's approximately linear, and that alpha is just called the temperature coefficient of resistivity. And you can see that on the table 18-1, that each of these have various temperature coefficients, and they tend to be really small. What makes the semiconductors strange is that, well, for the conductors, alpha is positive, and for the semiconductors, alpha is actually negative, which is sort of weird. So what that means is that for a conductor, the resistivity increases as you increase temperature, but for semiconductors it actually decreases as you increase temperature. Okay, so last time we talked about power, and I said that we have some formulas that relate charge or current to voltage. We have our capacitor relation. We have our resistor relation called Ohm's law. And we have a generic formula for power, which is that the electric power is P equals I times voltage. That's true for everything. And I made some comments about the fact that it's difficult to know how you're supposed to take Ohm's law and put it into this to know exactly what the power should be. Now, if you're given a particular current and a particular voltage, you know what the power is. And if you're given that a resistor has a particular voltage and therefore has a particular current, then you know what the power is. But figuring out exactly how changing a circuit will change the power consumption can be kind of difficult. So specifically I said that if you put this in here, you would either get V squared R, or you would get, wait, did I do that? No, whoops, I did that back. You'd either get I squared R, or you get V squared over R. And so it's not clear if increasing the resistance will increase the power, or if it will decrease the power consumed. And I just want to give you a little preview of what we're going to see in the next chapter, where we really start to talk about how to answer this question properly. We're going to talk a little bit, just a little bit, about resistors in series and parallel in advance of when we're supposed to talk about it, because I have no way of motivating the last relevant section of this chapter without first talking about it. So let's say that we're going to do our first circuit diagram. So you might want to draw this, you might want to write this down, because this will be your first time drawing a real circuit diagram. Let's say we have a battery, and we have a wire, and then it connects to a resistor, like that. And what this means is the resistor has some given resistance. We're assuming that these wires have no resistance, and for reasons that will be clear later, I'm not going to write this as V. I'm going to write it as a weird symbol, curly E. It will stand for electromotive force, and it's usually a symbol that we assign to batteries, to situations where a voltage is not variable. This is a fixed voltage source, and it always has a voltage between the two plates of curly E. And it's always going to be pushing the charges around, hence electromotive force. So the voltage difference between these two ends is curly E. Okay, and because of these lines here, this is positive and this is negative. So this top plate is curly E higher in voltage than the bottom plate. Now, this copper wire here is a conductor. It has some resistivity, it's very small. But if we look at the Ohm's law for the copper wire, if there's any amount of current flowing, as long as it's not too big, and the resistance is really small, the voltage difference is small. That means the voltage difference across from here to here is going to be really tiny. So roughly speaking, there's no voltage drop. And then if this point has voltage curly E, then this point should have also voltage curly E. And just for simplicity, let me ground the bottom here. And that grounding, it just means that I'm setting this voltage here to be exactly 0. It's harmless. It's very easy to do that just so that you have a reference point. And that means this voltage is also 0 because this wire has no resistance, so there can't be any voltage drop. So that means putting this battery here sets up a voltage difference of curly E, but it also means that we're imposing a voltage difference of curly E across the resistor. It's imposed. So this is sort of a bizarre thing, because previously we thought about Ohm's law as being a statement that if I have a resistor and I somehow force some current to flow across it, that there will be a voltage drop across the resistor. There will be a positive end and a negative end. And this end has voltage V plus, and this end is voltage V minus. And the voltage difference is V plus minus V minus. And the way to imagine what this means is that this little jagged line, this little ripple, is basically describing a very rough stream filled with rocks that water could flow down, and it's going downhill. And if you want to know what the potential energy of a single positive charge is right here, of charge Q, well, the potential energy right there is Q times V plus. So we could call it U plus because it's a higher potential energy. And the potential energy of a single positive charge here is Q times V minus. So a single charge that goes from here to here is going to lose potential energy. And then you might say, well, it's also being accelerated, right, by the electric current, the electric field, and then there's an electric force that's accelerating it. So it should also come out the other end with a large amount of kinetic energy. But that's not true. Because of the fact it's colliding with things, it never actually gains any kinetic energy. So there's only energy lost. And it's exactly that amount of energy difference, that energy lost, goes into the heat, goes into light, goes into sound if it's sizzling, goes into light if it's a filament in a light bulb. But mostly it's going to go into heat. And so instead of talking about the potential energy lost by a single charge, we can just say, well, I have V, which sort of generically describes the potential difference across the two sides, which generically tells me how much energy is lost. And in some amount of time, I have some amount of charges that flow through. So the total energy lost in some amount of time, the power, is just I times V. That's the meaning of that. Okay. Question? That's the meaning. Yes?
Wait, so I thought we said that a negative charge will have its highest potential energy near the negative side. So you're saying it's the opposite here? Like
This is I said it's a positive charge.
Oh, okay.
I said it's positive. If I were imagining negative charges moving, current flowing this way also means that really negative charges are flowing this way.
Oh.
But that also makes sense because a negative charge times the lower potential gives me a higher potential energy, and a negative charge times a higher potential gives me a lower potential energy because it's a sign flip. Okay, so it also works out. In that case, the electron is still going downhill. It's still going downhill, it's still losing energy. So thank you for adding that, that's exactly right. So this is why it's harmless to take what's called the conventional current, where it's positive charges moving around. It's totally harmless because you get the same answer, and you don't have to worry about sign flips. Okay, so that's the justification for P equals I times V. It's lots of little charges moving and going and losing energy, and then this is some, instead of worrying about every little tiny bit of energy that's lost, this is the total amount of energy that's lost in some amount of time. So that's kind of the logic behind it. Okay, so this was the argument for if you're forcing the current across, you would have a loss in energy, right? Or you would just say you would capture that generically, independently of whether or not the current is actually even flowing, as just a generic potential difference. And then however much current flows tells you how much energy flows. But this is kind of weird. It's kind of backward. I have a battery that is, say, fixed at 6 volts. And by hooking it up to a resistor, I'm forcing there to be a 6-volt potential difference. Which in turn means that in order for Ohm's law to be satisfied, a certain amount of current must be drawn out of the battery. So what this means is that so there is an imposed voltage difference of curly E on this side, right, just by hooking it up to the battery. Now again, this V means the potential here, this V means a delta V. So I'm being sloppy with notation, but this is entirely consistent with what's normally used in engineering and physics, and I dislike it. I dislike it, but that's the world I live in. I live in a world where we have to be imprecise to save time. Okay, so there is a potential difference of curly E across this, and this is the higher side, this is the positive side, and this is the negative side. That means there must be a current flowing across it, but the logic is backward. There's the voltage there first, and therefore a current is drawn so that Ohm's law is satisfied. And what that means is, if now I write V equals IR for this resistor, the current that's drawn out of the battery is V over R. But this V is the potential difference across the resistor. This V is the potential difference across the battery. It so happens in this case that they're the same, but in most of our circuit problems, they will not be the same. So that's why I specifically used a different symbol here, just so we're logically distinguishing between these things. And so that means the current that's actually drawn out of the battery is curly E over R. Okay, so there's some amount of current that will flow. And depending upon the voltage across the battery that you put there, a different amount of current will be drawn. The bigger the battery, the more current. The bigger and more resistant the resistor is, the less current will flow, because it's more resistant to the flow of current. So you might say, oh, okay, so that answers the question. More resistor, less current, but what if, so if V is fixed at curly E, then I can clearly see that making R bigger will give me less power. That's not entirely true. I'm going to show you now why that's not entirely true, and I'm going to dip into next chapter to talk about slightly more complicated situations, because I need to motivate what happens in your house and why your house is set up the way it is, and certain precautions you need to take with electrical stuff in your house. Okay, so first, imagine I want to put a bunch of resistors together. I want to start adding resistors. So now let's say I have a similar circuit, but I have a bunch of resistors, all in a line. The battery still has the same voltage difference, only now I have a bunch of resistances like this. Okay? I could ground it, but I think we're past that now. We can move on from that. Instead, we can just observe that there's still a voltage difference of curly E between these two plates, which means there's a voltage difference of curly E between the top and the bottom wires, which means there's a voltage difference of curly E between this point and this point. Now, that doesn't mean that there's that voltage difference in between like that. That's not what it means. However, I'm just going to say, okay, so this is a voltage difference of curly E. I'm just going to say, without any loss of, I'm just going to say that it's obvious that this is equivalent to having a single resistor whose